So we want to go outside, create another geometry container, and let's turn off these two for now. This will be our pop network. So inside, let's take an object merge, and we want to take from fx outman source and also the other one, so woman source. And we want to merge these two together, so we will handle the particle simulation all in one DOP network. So basically we want to emit not on the mask but on the edge where the red part is. So before doing the pop simulation we will write another cache just with the polygons that we will emit the particles, because right now is almost 400k of polygon and it will be pretty slow for the particle simulation. So before doing that, let's take a polygon angle. This will be erase. And here let's just create a float variable, let's call it thres for threshold, so chf threshold, and we want to check if the current age is less than threshold, then remove point, on geometry 0 the current point number. If you click here and set it to something like 0.2 and write correctly the name, and we want to write this out because it will be much faster for the particle simulation. Also we can delete a few attributes because basically we don't need any attributes on the particle simulation, so delete the age, the mask and the UV also. We shouldn't have anything on the details, so just the position. And finally, since the particle will be emitted with some force that will push out of the mesh, basically we could have some problem in the areas where the two mesh are touching each other. So before caching out for the particle simulation, I want to take a VDB from polygon for both of the mesh. So let's plug this for the man and let's set it to 0.06. Copy it and plug it to the woman mesh. And also let's do a VDB reshape. Plug it to the first one. Right click, action, reference, copy and plug it to the second one. And this will be fed into a VDB combine. So one on the left, one on the right, and we want to set it as a SDF intersection. So basically we want to delete the parts that are touching each other or too close to each other. And we can use this reshape to increase or decrease the values. So I want to set it to something like 2. And before the cache, let's take not a group delete, a group node. So we can use the node VDB. We need to convert the VDB back to polygon. So here we want to convert to polygons. So we have something like this. And this will be on the second input of the group. So the group, we want to set it as points. Let's call it erase. And don't use the base group. We want to use the bounding object. So now we can delete this part that could be problematic for the simulation. So let's take a delete node and just delete entity points, group, erase. So let's take a file cache and we can write the sourcing for our particle. So let's call it pop source. This will be time dependent, explicit, and I want to save it in the job variable cache $os / $os $f4. I always forget the frame, it's really funny when it happens. .bgo .sc and save to disk. So it took something like 3 minutes on my system, but the broad cache is really light, not even 1 megabyte, and it's super fast to scrub. You can imagine that this will be very fast to iterate in the pop simulation compared to the uncached one. and we won't scatter on the surface, we will use point, so let's take a scatter node after the cache. And here we don't want to use the force total count, otherwise when we have smaller area for emission, the points will, the count is based on how much surface I can scatter on and not on how much large is the area to scatter. So we want to disable the force total count and use the density scale. So it won't clump the points together when we have small emission areas. And we don't need a density attribute, it will just work in a uniform way. And we also want to change the global seed with the current frame number, so $F. And for now, let's just lower it to, let's say, 4, so we have less points. So we can drop down, let's use a pop network, so we already have a few nodes available inside. But before diving in the pop simulation, I want to have some reference to the camera. I don't have a camera on the OBJ context, I created directly here on the stage. And we can bring it here with this lop import camera node. So we want to pick the camera on the lop path. And here on the primitive path, we want to take the camera 1. So, okay. And we should have it. And we do. So now I have some reference. And also, basically this time we're going to use particle, but to instance something physical, which is petal flowers. That means that I don't want to animate the p-scale, or rather, we will animate the p-scale at the start of the emission, but we don't want this particle to disappear or to scale to 0. We just want to be swept by the wind off the frame. So basically I want to create a box that will delete all the points outside the camera. Take a box, let's template it, and let's see, where is it? We want to basically include everything which is in the shot. So let's set it to, let's say, 24 and 2 for DZ. Let's make it something like this, 32. We will center it a little bit, and we need to include all the heights. So let's make it like 22 and center it on the 0. So path relative reference divided by 2. Basically, we want to encapsulate all the area of the simulation. And let's append a null after the box. We will call this pop kill. So now we do have a volume to delete the particle. Now we can dive inside the pop network. Now, inside here on the pop source, let's change the emission type to all points. We don't want to scatter on surface. And let's see, we don't have velocity yet, so let's disable the guides, and we should see some still points. Yes, they are. And basically, let's start to introduce some force. We want to start with a pop wind, so drop it after the source and enable the guide. So if we increase the velocity, we can see where the wind is blowing. And we want to set it to 1 on the X and let's say 0.6 on the Y. So it will push this way. Let's see. Yeah, we want to move the particle that way on the left. Let's increase the velocity, the wind speed to 2. So it's more present. And we are basically done with the particle simulation. No, I'm joking, this is terrible, there's a lot of work to be done in here. So, as you can see, right now the particles are living forever, so we want to introduce that volume we created to kill the particles. So let's take a pop kill, we will place it as the last node of the stream, and we want to enable the bounding and bounding object, and we need to take the pop kill that is coming from the box. So accept. We do have this thing, and I believe it's in reverse now. Yes, it's deleting everything inside, so check invert. and now the particles should be deleted as soon as they reach the edge of the box. And yes, they are. And I want to go outside, maybe lower the density scale even more for now, so we can see better what's happening on the points. And let's see, inside the solver, we want to add some noise to this wind. So if we close up on the guides and we start to increase the amplitude here, we can introduce some noise on the wind itself. So let's set the amplitude to 2. And I want to increase also the swirl size to, let's say, 4, so it will be more smooth. And also the pulse length. Right now is too fast, so I want to set it to, let's say, 10. So it will be very slow, something like this. Now, even if we introduce some noise, the wind is applied with the same magnitude to all the points. And typically, when you're working with particle simulation to randomize the effect of a force, you use some random factor, maybe with Vex expression. In this case, we still want to instance something physical, so there will be petals that are actually bigger than others, so we don't want to randomize how much the wind affect these petals in a random way, because if we have a bigger petal than another one, that petal should be, influenced less from the wind. So this time we want to calculate the mass before the simulation. So we want to go outside, and before the scatter, let's drop down a point angle. We will call this init at. We will use this also to initialize other stuff that we need for the simulation. So to tie the mass to the actual, size of the petal, we just want to tie to the p-scale. So basically we need to compute a p-scale before the simulation. We can tweak it later, but always in a manner that will be coherent, so less p-scale, more influence on the forces. So float p-scale, we will feed 0,1, and here we can randomize by point, so rand on the ptnum, and we want to remap it by a CHF p-scale min and a CHF p-scale max. And we can take a copy to points to see what will actually be the sides. So after the scatter, let's take a grid, just 2 by 2, and make the sides 1 by 1. So it will be consistent with the final size of the particles. So right now we do have something like this, and let's see why it's not taking. Oh, we need to bind the p-scale. So f at p-scale is equal p-scale, and we do have something like this. So the p-scale will be, let's say, from 0.1 to 0.2. We don't want that much of a variation, something like this. And to compute the mass, technically the mass is computed with the volume, but we basically have a 2D surface. So we can say that the F at mass will be equal to the p-scale by the p-scale. So we can factor by 2 the sides and using to drive the mass. So if we go in the geometry spreadsheet, we should have both the mass and the p-scale. And now we want to go back in the DOPNet, and here we want to deactivate ignore mass. Now the particle will be, I guess, super fast. Not that much actually, but basically we want to decrease the air resistance, so 0.0.1, a very low value. And as you can see, some particles are reacting quicker than the other. It's not that much, we still need to add a lot of forces, but that was the core of it. We need some mass so we can differentiate, but still tying the simulation to the actual size of the petals. Now we want to introduce some initial velocity. Here we are inheriting the velocity, but we don't have any on the points. Now we will introduce both some velocity and some angular velocity on the points, but To do that, basically we need to compute a couple of vectors here in the init attribute. We need the usual vector that we can use to build some local frame, one pointing outside the mesh and one which is tangent, so we can use some neighbor point for this. So the two vectors we need, it's the v at v for the velocity, and we can take the normals of the points. That we don't have it, but if you explicit write it like this, the normal will be automatically built. If we create the visualizer, we should have, the classic normal on the velocity. Let's decrease the size of the vectors. And for the other one, basically we want to take one of the neighbor positions, subtract it from our current position, and we end up with some other vectors. So first we need the point number of the neighbor. So let's create an integer variable. We will call this Flanders because it will be our neighbor. This time we just need one neighbor, so we want to use this version of the function, and the neighbor that we'll find will be based on the point number, so in this case will be basically random, which is perfect for us. So geometry 0 from the current point number, and just give me the first point you encounter. So now we can create a vector variable. We will call this axis, and we will take the position of Flanders, so point 0 p of Flanders, and we will subtract it the current position, and we want to also normalize it, so normalize and semicolon. And if we bind it to this new attribute, so v at axis is equal axis, create the visualizer, and it will be color, of course, so vector, make it like green, and we do have a random tangent vector, and that's all we need from the init attribute. And I keep forgetting about increasing the wrangle size, sorry about that. This is basically the init attribute, and if you miss the erase, is this one. If you know a way to make the wrangle size as default, just let me know in the comments, because I didn't find a way and I keep forgetting about that. Anyway, let's drop down a point VOP after the init attribute. We will call this set v and dive inside. Basically we want to, let me disable the axis, we want to use a noise to randomize both the magnitude and the orientation of this velocity vector. And the noise we want to use is an anti-aliased flow noise. And basically you can use this noise with a 3 vector like usual, but what we want to do is to use a 4D noise as source. Basically we want to, where is it, the vector to vector 4, we want to plug the position and append the time to the position. So we end up with a vector 4, and we want to plug this as source of the noise. And we want to multiply basically the incoming velocity, the one that we define from the normal, and multiply it for the result of the noise. And this will be our new velocity. Now, by default, this noise go from negative 0.5 to 0.5, so we want to fit it from negative 0.5, 0.5, 0 and 1. And basically, since we are using the time as a 4 component of the noise, this thing is already animated. Maybe it's not visible at the moment. Let me drop down a time shift and freeze on, let's say, frame 88. You can see that the magnitude is actually animated on the time. We want to multiply the time so we can have control on some sort of speed. So the time will be multiplied and then will be appended to the vector 4, and we want to promote this parameter. We can call it speed, so this will control the speed of the noise. Basically now it's 0 and it's not moving. We can set it to 10. We will have a really high frequency noise. I mean frequency intended as speed, sorry. So back inside we randomize the magnitude, and of course you can play also with the frequency, the roughness. I will leave it just as it is, and just to make more compact I will click here so it will collapse all the stuff that I don't want to see. Also we want to be able to control the min and max, but I don't want to do it in this fit because from here we will branch out for randomize the orientation. So I want to take another fit range. And on this one is already going from 0 to 1, but we want to promote the destination. So here let's call it max speed. So max, I mean this is not the speed of the noise, let's call it max v. So max v and min v. So outside I can set it not to be collapsed to 0, but let's say from 0.5 to 1. So something like this. And I don't want this speed as 10, let's say 0.4, very slow. Now to randomize the orientation we want to do the classic quaternion operation actually, but this time, if you followed my video, I usually do it inside a wrangle. This time we will do it inside a point box. So basically we want to rotate this vector before feeding it into the new velocity. And we will use the classic qrotate function, so rotate by quaternion. The product will be the incoming vector and the result will be the final velocity. Of course we need a quaternion, so let's create a quaternion node, and as usual we need an angle and an axis, and this will be the quaternion. Now the axis is the axis vector we calculated outside, so let's just take a bind attribute and retrieve the axis, which was a tree float. And right now, as you can see, the error, we have no error because we do have the correct function, but we are not providing any angle. Like if we take a constant and we increase it, you can see that the velocity is rotating on the axis vector. So let's delete the constant. We don't want to use a constant. We want to use some angle value from outside. So create a parameter. We will call this angle and ang for the name. And basically we want to take the output of the first fit, which is going from 0 to 1, and fit it between this angle that we will decide from outside. So take another fit. This will be the value. And the maximum and minimum angle we will decide it here. So the maximum will be the destination max, so the positive, and let's just multiply by constant for the minimum. So we will multiply it by -1, and this will be the destination minimum. So this will provide the angle of rotation. And of course it needs to be in radians, because we will decide this in degrees, then it will be converted to radians. So now from outside, if everything is done correctly and I set this like to 45, the velocity are rotating using that noise and fitting between negative 45 and 45 degrees. So this is basically all we need for the velocity. Now, just to be consistent, let's also normalize the output of the qrotate, so we can also update our normal in a correct way. Not even sure that is needed, but just to be correct. So if we check our simulation and what's happening with the new velocity, let's see. Disable the wind so we can have a good feedback on just the velocity, and it's been passed. Maybe also increase it. Let's make it double, so like 2, and let's check from the camera. Enable also the wind, and on the wind we can disable the guides now. So we do have something like this. Now, if we replace the copy to points with the result of the simulation, and also let's merge it with the mesh, so let's take the both of the meshes, plug it here. You can see that also the initial orientation is wrong. Typically, you will rotate the grid by 90 degrees, also compute an up vector, but the main problem right now is that the particles are not spinning at all. So we need to introduce something called the angular velocity, which is expressed as W. It's a vector like the velocity, so not normalized. But the problem is, even if let's take a point angle before the scatter, even if we set this angular velocity, so be at W like set, I don't know, 4, 6, 1, it should be computed by default by Houdini. But if we check the particle simulation and let it cook, let's see the grid, they are still not rotating, even if we plugged a very high amount of angular velocity. This is because Houdini, in order to make the angular velocity work, needs the orient attribute, which is a quaternion. The normal and up vector wouldn't be enough, so we need to compute this orient. Let's rename this triangle to calc orient. And in here, the first thing we want to do is to retrieve the velocity vector, or rather the normal, and the axis vector we calculated here. So let's delete this line. Basically, if we take, let's take this bunch of points. Imagine that this one is the point of example, and look at the axis. Basically, we want to say that the normal is the y-axis for that point, the tangent is the x, and the cross between these two will be the z. This will provide basically three vectors that we can use to compose the orient attribute. So, vector x, it will be v at axis, vector y, it will be v at normal, and vector z, we need the cross product between the two of those, so cross between y and x, and normalize it, so normalize cross between these two. Now, we have three vectors. Basically, we want to create a matrix 3 by 3, so matrix 3, let's call it M, and we want to set with x, y, and z. And basically we are creating a 3 by 3 matrix which can express both rotation and scaling, but when it's normalized is just a rotational matrix. So we can use this matrix to create the quaternion. We usually create the quaternion providing an angle and an axis, but as you can see, you can also create a quaternion with a 3 by 3 matrix. So the P at orient, P is used when you need to declare an attribute as a quaternion. It will be equal to quaternion using the matrix with the axis we provided. So we don't have any angular velocity now, but let's provide it one just for testing. So V at W is equal set, let's say 4, 7, 3. And something should happen in the simulation. Let's zoom out and let's see. Let's hide these guys. And as you can see, they are spinning. Too much, but they are spinning. And the cool thing about the orient attribute is that it will also orient the grid in the starting orientation correct. So I want it aligned with the mesh, so this is correct for me. Now, of course, we don't want to calculate the angular velocity like this. This will be equal for all the points. We want to do it inside the set v point VOP. So dive inside here, and let me rearrange this thing and come back. So the final bind won't be here on the geometry output. We need to bind export to W, which is a 3 float. And we don't care about this part, we don't want to use a noise, we want to use some random value for the angular velocity. So let's duplicate the geometry input because we need the point number. And we want to use the point number to generate 3 random values. So 1 and duplicate it 2 times. And we want to add some constant value, so we can basically change the seed of this random number. So let's put some height value here, duplicate it 2 times, and connect it to the random. So this will give us 3 random values. We want to use these 3 values to compose a 3 vectors, so float to vector, 1, 2, and 3. And we want to ultimately fit this value between some minimum and maximum we want to be able to define from outside. So this will be the value. We want to promote the destination minimum and maximum. And let's call the maximum max ang v and max w. And the minimum min ang v min w. So we do have the control from outside, and this will be binded to the W. So from outside, let's say that the minimum angular velocity will be 1 and the maximum will be 2. And even if we are providing all the same value here, this is just the fit. The seed is different because we provide a different seed for the random number. So basically now the particle should spin in a different manner from each other. And they are. Now the only thing is that they are basically spinning all in the positive or clockwise direction, because the output, I mean the minimum is 1 and 2, so no petal is rotating counterclockwise. I don't want to fit this value between like -2 and 2, because that will provide us also some very low value near to 0. I don't want this. So another way to do it and keep only the, let's say, the highest value, both in positive and in negative, is to just take half of the point and flip their angular velocity. So in here we want to create another random value based on another seed. So let's set this to another number, and this will be fed into a compare node. So now we have a random value between 0 and 1, and this compare will check if this value is greater than 0.5. So basically we will take half of the points and reverse the angular velocity. So right now we have either 0 or 1, we need either -1 or 1. So we want to multiply by constant, and we want to multiply by 2, and then just subtract 1, so add constant -1. So if we take the output of the fit and multiply it for this final add constant, now half of the point have the negative angular velocity. We can quickly check it. Let's filter W. Right now we have both positive and negative, but we don't have, as you can see, from 1 is skipping to -1. If we don't multiply this guy, we only have positive value. So I don't want to create a box. Now we have the correct spinning behavior, almost. We still need to add something inside the dopnet. And of course we need to delete this time shift because this is freezing our mask animation. So let's quickly check it without. Yeah, we do have the correct thing. Now, inside the popnet, first let's add some other turbulence with a pop force. So let's take a pop force node, and we will leave everything as default setting. We just want to introduce some amplitude, so let's set it to 1, and this will add some other turbulence. Yeah. Now, a big thing that is missing right now from the simulation is some drag. We do have some high resistance calculation going on here, but there's no main drag on the particle. The thing is, if we just use a regular drag, inside the calculation you are not actually using this as a mesh, but rather a sphere. Basically, this is what happened inside the calculation of the popnet. So the drag is uniform all over the mesh. In a case of a petal, or let's say a grid for now, in this axis, the drag where the surface is wider should be much higher compared to the drag applied to these sides, because here there's nearly no air resistance. And so to do that, we don't want to use a pop drag, we want to drop down a pop property and plug it after the force. Here you can actually define a lot of attributes here, but what we're interested in is in the dynamic tab and is this drag shape. This is basically the local axis of the, imagine this sphere used by the pop net. And what we want to do is actually to have the drag shape 1 on the x and z axis of the grid, but we want to set it to something like 100 on the y axis. This will say basically on the y axis of the point, you will apply 100 times the drag coefficient. So we should really see some difference now in the simulation. And we do. You can see how they are keep accelerating and decelerating based on actually which side they are facing the force. Let me plug back the grid. You can see that now it's really changed the simulation. And also we want to enable this drag center. This is basically the center of rotation of the grid. Set as 0 like this means at the center of the grid. We want to enable the expression and override this parameter, which is called drag center. So drag center, it will be equal. We want to just randomize it a little bit from the center. So rand over the at ID. We can't use the point number because now we are inside the popnet, so the point number will change. And we want to multiply by a really tiny amount because the 1 means the edge of the surface, so multiplied by 0.01. This will offset just a tiny bit the center of rotation. So we can't really see it until we, something like this. Also, we want to apply some drag to the spinning because this drag is applied only to the, the velocity, not the angular velocity. So we want to take a pop drag spin this time, plug it after the pop property. And here I believe that by default, this other node, by default it should be way too much. I believe that this completely stopped the spinning. We want to set it really, really low, always because we are using the mass at this point, so 0.02. And this will apply just some light drag to the spinning property of the petal. I believe this is pretty much good enough. We just want to apply some final wind to the older particles so they can get fuck out of the frame quicker. So back inside the popnet, let's put it before the pop property. We want to drop down another wind. We don't want to modify the main one. And this will be set to, let's say, 1 and 0.2, so it will push even further on the right and a little bit on the y-axis. And let's set the speed to 4. So right now it should be really strong. And of course it's applied to everything. And this time we don't care about the mass, so leave ignore mass on, but we want to enable the expression and we want to base this on the normalized age. So the parameter we want to modify is this wind speed. So wind speed, we want to multiply this for a ramp, so ch ramp, let's call it wind ramp, and it will be based on the normalized age, which should be already written by default in the popnet. So right now, basically the particles are getting dragged by the wind as they get older and older. So basically in the beginning no effect, and as they grow, but I just remember we didn't set, we need to change this life expectancy. Even if we are deleting particle, if we are using age, the age is based on the life. So let's set it to 10. And now the wind will actually have some effect. As you can see, they start accelerating like half life. And for the ramp, let's just set some more smoothing. Let's say something like this, so they will start really slow in the frame and then out. Yeah. And finally, before caching out, we want to introduce some collision with the mesh, because right now there's no collision. The particle, they are emitted, let's say here, they immediately enter the both of the mesh. This is not good. So let's copy one of these VDB from Polygon. We want to plug both of the meshes this time, something like this. And we can lower the resolution, so let's say 0.1. Let's plug it to a null. This will be out collide. And also let's drop down a VDB reshape so we can shrink it a little bit. Switch the operation to erode and visualize this guy. And here let's increase it to, let's say, 2. Then we want to go inside the popnet, and in here first let's take a static object. We want to merge it with the pop solver, so 1 and 2, this will be the final output. And here we need to say on the collision, let's enable the guide, and we want to use not ray intersect, we want to use volume sample because we are using a BDB. The proxy volume will be the out collide. And you don't need to plug a mesh, you can do it, because if you disable this, you don't have any mesh visualized here, but honestly it doesn't matter that much. And right now, collision should already work. This will slow down the simulation quite a bit, but still manageable. We will need to increase the points amount before the final cache, but we can clearly see that collision is happening. The only thing we want to change is on the pop solver, go on the collision behavior. We don't want to be an unchanged response, we want to slide on the surface. So they will use the friction parameter they have to slide on the mesh. Yeah. So we should be set to cache the particle simulation. Just let's increase the scatter amount to the final scale you want. I set mine to 10. So this will give us the final emission amount. It is working, yeah. And also we can delete the axis and the normal attribute from here, so it will be lighter in the simulation. Normal and axis, go. So it should be still pretty manageable. And let's see, we have something like 100k. Yeah, it's good enough. Let's copy one file cache. This will save the simulation. So not after the popnet, but we want a dop import node that will point to the popnet, and we want to take the pop object, even if we have just that for now. And also we want to delete a lot of attribute after the simulation. Here basically delete these two, set to non-selected, and we want to keep the age, the life, the ID, the orient, and the p-scale. These are the attributes we care for. And also let's take a group delete, because I believe we have the stream source input. Delete any group. This will be pop sim, and this was already set to take the OS name, so the path will be correct. And let's do some organization things up here. So pretty messy. This was just for visualization. We can delete this guy. And maybe turn off the relax iteration. We don't want to relax the points. So we should be all set, and just save the simulation. Alright, it took a couple of minutes on my system, and the size also is pretty manageable. It reached something like 3-ish megabyte at the top, because we do have some attribute on the mesh, but we need on the points, but we need those attributes. And basically we are done now for real with the particle simulation. We will fix a few things later on, but for now let's move on the petal. And basically this will be just a little grid with a little Copernicus texture applied on it.